Well, if you're like me, especially in the springtime, you want to know if it's going to do this. Da, da, da. I'm like, well, name what that is. Of course, that's rain, right? Well, rain starts with a cloud, and within the cloud, I told you just a minute ago that that is liquid water. And how did that liquid water come to be? Well, basically gas liquefied. So at what point will water vapor become liquid water? Well, like this says, basically when that happens, when condensation happens, which is what that is, hydrogen bonds are being formed between water molecules. Well, I bet this makes sense to you, and you've seen this before. We're going to talk in a minute about humidity. Humidity is basically water, how much water vapor there is in the air. And in high humidity, okay, you figure, and I'm not going to take the time to draw all these, draw out the H2O molecules, but if these are my H2O molecules, okay, in high humidity, doesn't it seem like they're just itching to go ahead and form these intermolecular bonds, okay, so to go ahead and become a liquid. So that makes sense, right? The other thing is if the temperature is relatively low. So high humidity is a player of getting water to condense. The other thing is, and I don't know how to necessarily show this, I'm just going to kind of show the three physical phases here. Solid are close together. Here's my solid, liquid, gas. And liquids are a little farther apart, and gases basically have no interaction with each other, so they're very far apart. We say that this has lots of KE, lots of kinetic energy, lots of motion, and this has the least amount of motion as a liquid. And that would include water as a liquid. Now, so here's the deal. Lots of kinetic energy would be favored at high temperatures. Oops. High temperatures, and solids are favored at low temperatures. Okay, so I'm sure that makes sense to you. So bottom line is, if you are trying to get a cloud to form, here's my cloud, what you need is high humidity and what? Low temperatures. And so those both kind of work together. So here I've got a series of boxes to kind of walk you through. And in each one of these boxes, kind of think of, we kind of allow time to do its thing. Here we have liquid water, and here we have basically no water, no H2O. And kind of think of this as like a barrier, like a saran wrap thing there. Notice that your chamber has a temperature of 20 degrees Celsius. You'd be like, well, why is there no water? Well, we just made it so. And again, I've got a barrier here so that none of this liquid goes ahead into its gaseous state. Now, in these three little things, I want you to notice that up here we have a pressure gauge. Now, gases, so H2O gas, okay, exert a pressure, and they kind of make sense to me because if there were particles of gas in here, they're banging against their container in all directions, and that pressure actually then can go ahead and make this needle deflect and show a pressure. So that's kind of the situation. Now we let a little bit of time lapse. We remove the plastic wrap. Okay, so now it's open, and now we have a little bit of this liquid, some of this liquid going to form gas. Okay, it just will. Like if you've ever had a cup of water and let it set out, especially if you have a cup of water with a big hole on the top, a lot of surface area, that water will evaporate. And so that's exactly what we have going on here. So we still have liquid, but now we've got some gas particles. And notice now what happened to your gauge. Okay, your pressure gauge is starting to show those cute little water vapor particles deflecting that. Okay, so that's the first one. And then the last one, excuse me, looks like this. Where now we've let a little bit of time do its thing. If you're familiar with the concept of a terrarium, so we have liquid down here and gas here. If you compare the two, notice what we do is we have more gas particles here. What a terrarium does is basically you have a closed system, and you can kind of see the water, the water kind of beating on the container. It kind of it sweats kind of in the inside. Okay, water is condensing. Okay, and the sides of your container for your terrarium. Here we're showing water condensing. Okay, what does condensation mean? It means go from a gas to a liquid. Here we have water still evaporating, all within our same system. Notice that we have more gas particles. We had, what, 4 over here, if I count those. And here we've got, oh, it's hard to tell. Maybe, I think they're just trying to show you 5, because basically we have 5 evaporating and 5 condensing, so it's kind of a wash. I'm not sure. It's either 5 or 10 here. But notice that we have, maybe it is 10, we have more deflection. Okay, this is more, showing more pressure here on the pressure gauge. Now this could be a very special place over here, here on our last scenario over here on the right, because this is showing you that 5 is evaporating and 5 is condensing. That's at what we call equilibrium, when the rate of evaporation, shown as 5 here, is equal to the rate of condensation, also shown as 5. So at equilibrium, we say a few things. We say basically the air is saturated. Saturated. Now, I bet you've heard of, or we'll talk about relative humidity coming up, but I bet you heard of 100% relative humidity. Okay, that means the air is saturated, and basically you have maxed out your H2O vapor. Okay, no more H2O vapor can be fit into that box. I want to, though, point out something very important. Even though no more than, I guess it is maybe 10 here, even though no more than 10 water molecules can be in this chamber, notice that we have an ongoing process of evaporation and condensation. It's what we call dynamic. It's not static. But the same amount that is evaporating is equal to the same amount condensing. So that is, the air is what we say saturated.